So let us review the problem. So we are considering this reaction diffusion equation on the domain 0, 1 with zero flux Neumann boundary conditions. And so we are particularly interested in the qualitative behavior when sigma is varied. Okay. So let us remind some computations that we did the previous sessions. So we'll switch to the blackboard. So in order to study the system, which is linear, a good thing that we've done is to make the projection on the eigenfunctions of this operator. Okay, so from that we obtained an infinite systems, 2D linear systems, which write UK prime VK prime equals UK minus VK minus lambda K sigma UK and 3 UK minus 2 VK minus lambda K VK. And in order to do that, we say that we look UXT as the sum of K going to 0 between 0 and infinity of UKT VKX. And the same thing for V. And Vk satisfied that Vk. So this is the derivative with respect to x equals minus lambda k. Vk, we have Vk, Vj equals 1, equals 0, or 1 if, so let's write. So the integral between Vk and Vj is 0 if Vk is different of Vj, and it's 1 if k equals j. So we can write it as Vk Vj. We wrote it the Kronecker sign. And what else? Yeah, so write it here. Sorry, I have not space. Vk prime of at 0 t equals Vk prime at 1 t equals 0. Okay, so then we have the equivalence that studying the PDE is equivalent to study all the EKs here. The interesting thing here is that we can do qualitative analysis that we know for ODE systems. All right. Okay. So next. Yep. All right. With that in mind, so we did this exercise, and we showed that. So we study all the EK, and we show that in fact for each K, when vary sigma, there is a qualitative behavior. In particular, EK features a bifurcation from a sink to a saddle point. when sigma crosses a certain value sigma. So we can remind that also. So let's write again now EK here. So I write again my system EK here, which writes UK minus VK minus lambda sigma UK and VK 3 UK minus 2 VK minus lambda K VK, or equivalently, it's UK prime VK prime equals 1 minus lambda K sigma UK minus VK, and here 3 UK minus 2 plus lambda K VK. So a thing that we studied last time is that so if I call AK the matrix associated with this 2D ODE, the trace is equal to minus 1 minus lambda K sigma plus 1. Which is negative because I recall here that lambda K is B square K square. And the determinant of AK was 1 minus lambda K sigma minus 2 plus lambda K plus 3. So I can also write it as, I will keep my sigma here, so as sigma lambda K top 2 plus lambda K all right, minus 2 plus 3, which makes 1, and I miss minus lambda K. So as you can see, if I look the values of sigma for which this quantity is negative, I obtain exactly, let's do it here, that determinant of AK negative is equivalent to sigma less than lambda K minus 1 divided by lambda K 2 plus lambda K, right? So, and this value, I called it sigma K, so it is lambda K minus 1 divided by lambda K. All right, so as sigma crosses this value from the right to the left, the system EK, the stationary point 0, of EK goes from a sink to a saddle node. All right. So the next thing is I asked you the last time to check that, in fact, the sigma k, the sequence sigma k is decreasing. So in order to do that, you just have to study the variations of the function x minus 1 divided by x divided 2 plus x. So for example, you can take the derivative. So I get x 2 plus x minus x minus 1 divided by this whole thing square. So note that the lambda k are positive. So I'm just interested here in the positive values of x. And so this quantity, I can write it as x2 plus x minus 2 x squared minus 1, which gives me finally minus x squared plus 2x plus 2. Yeah, so if I compute here the delta here, I got 4 plus 8 equals 12. So this has two roots, which are so it's let it right here. So it's minus 2 plus minus 2 square root of 3 divided by minus 2. Okay. So this is 1 plus minus square root of 3. Okay, anyway, so I see that this polynomial here, the derivative of f prime, is negative for x greater than x2, and I can check that my sigma case here so my lambda case are greater than lambda 2, that x2 than x2. So okay, so for all k, my lambda k are greater than x2, so which proves that the sequence sigma k is decreasing. All right, so now with that in mind, let's come back to All right. So with that in mind, let's review these things. So first, now we have a value sigma. We're looking at the dynamical behavior for a fixed sigma. So depending on the value of sigma, when sigma crosses sigma k, my ODEs go from a sink to a saddle node. However, for a fixed sigma, for a fixed sigma, only a finite number of systems EK are not a sink. So we are going to review this thing. Just let us have a global picture of the thing. So the sequence sigma k, so exercise 5, I let you think about that. I'm not going to do that here. So we just proved that the sequence sigma is decreasing. And now look at the proposition 4. Suppose that sigma is less than sigma 1. And suppose that the initial condition is not the origin. Okay, so 0, 0 is a saddle for EK. So for this EK, so if UK0, VK0 does not lie in the stable manifold associated with EK, then the L2 norm of the solution of the PDE is going to plus infinity. And also, if sigma is greater than sigma 1, then for all initial conditions, the norm of UV in L2 is going to 0. So that's what we are going to discuss in the, at least in the first part of the session today. Okay, so let's review more in detail the proposition 3 and proposition 4. So the proposition 3 just states that it says that you have EK. And so you have sigma k, and when sigma crosses sigma k from right to left, so 0, 0 goes from a sink to a saddle. So this comes just from the computation that we did, and because as sigma crosses sigma k, the determinant of AK goes from positive to negative. All right. Meanwhile, all the sigma k for all k belongs to 0, sigma 1, and as k goes to infinity, sigma k goes to 0 plus. So when you pick up a value of sigma. So if sigma is greater than sigma 1, for all k, 0, 0 is a sink for EK. So we expect that the PDE also is going to 0, 0, because all the EK 0, 0 attracts all the trajectories of EK. So we expect that that's the same for the PDE. Now, when sigma crosses sigma 1, 0, 0 is no more a sink for E1, it's a saddle. But all the other are still a sink. And then the same thing for E2. So as you decrease sigma, you have more and more saddles, but for most of the systems, you have a sink. So we expect that that gives what information that we expect that only if everything goes to 0 for the EKs, we expect that this won't be taken so much in account for the PDE. Okay, that's the idea. Now, since we are dealing with infinite dimensional systems, we have to be rigorous. So now, for proposition 4, so now we fix EK. So assume that, let's work with 1. Let's work with K equals 1, and the same thing works for everything. Let's consider E1. So if I have a saddle, let's assume that we have a saddle. So for a saddle, you have one eigenvector vector. So if I start here or here, I'm going to 0, 0. This comes from the qualitative analysis of ODEs. But anywhere else, the trajectories go like that. So what does it say? If so it's U1 0, V1 0 does not belong to here. So if I don't pick up my U1 0, V1 0 here, so let's call it this. Let's call it V1. Then what can you say for the norm of U1? The norm of U1 V1. Does somebody can tell me? Oops. Can somebody tell me what's the limit of U1 square T plus V1 square T? If my initial condition is not here on this yellow space, which is the attractive manifold of 0, 0. Well, if I don't start here, I'm going to plus infinity. What do you deduce for the norm in L2 of the PDE? You know that UK square plus V square is equal to but since we have that, we know that is going to plus infinity as T is going to plus infinity. You agree with that? Well, you should agree. So we have just explained what is the meaning of the proposition 4. So we did for k equals 1, but then when you decrease sigma, the same thing is valid for sigma k. So it tells what it tells that as soon as sigma is less than sigma 1, you have a great chance that your PDE is going to infinity. So since we work with PDE, we have to choose a norm. Here, we work with the norm L2 because of the structure of the Hilbert space associated with the scalar product and stuff. So next, we're going to deal with theorem 1, which says that if sigma is greater than sigma 1, then UV goes to 0. So you see, you have a bifurcation here. Things change. For sigma greater than sigma 1, everything goes to 0, but when sigma crosses sigma 1, your PDE is most likely to go to infinity. All right, so next we are dealing with in more details with this theorem 1. So now if sigma is greater than sigma 1, then for any initial condition, so I need to start in L2, then UV goes to 0 as t goes to infinity. So there's several ways to look at that. Let's start with 1. So I just give some ideas here before to give the real proof, because it's interesting to do that. So so first I could look at let's just take the PDE. So if I look at the derivative of so 1/2 of the integral of u squared plus v squared, but since I will put the 3 here, and I derive with respect to t, so what I get is the integral of 3 u squared minus 3 sigma ux So the 3UV cancels with that, so I obtain yeah, so this is a classical thing to do here, but here I don't have nothing because of the 3 here. So this doesn't work. But another idea, I'll do it now for the UK. So UK prime equals U minus V so I have 1 minus sigma lambda K UK minus VK prime, so 3 UK minus 2 plus lambda K VK. Now, if I do the same thing, I got something. So if I look at 1 divided by 2 dt of 3 UK square plus VK square, I will get it's lambda K. And now here I have a result if for if sigma lambda K is greater than 1, then from that I can have my result. So, and to ensure that sigma lambda K is greater than 1, it's so for this, it is sufficient to have sigma greater than 1 divided by lambda 1. Okay, but that's not optimal. So I have already this result with this simple computation, because after I can take the series here and I can obtain that. So I let you think about that. I have the result here, but that's not my theorem. My theorem says if sigma greater than sigma 1 and sigma 1 is smaller than that. So this is not the best result, but it's already a result. So now if I want to match the result of my theorem, we need to study more in detail the eigenvalues. So this is here, this is a Lyapunov function. Now, if I can take the series here, let's take another color here. If I get that, so the 0 is not a problem. So I can take the series here, and I will obtain something negative in front, and from that I obtain the result. I let you think about that, okay? But that's not optimal. So if now I want to prove the theorem, I need to study more in detail the eigenvalues. So as a reminder, my trace of AK is -1 minus lambda k sigma plus 1. My determinant is, for example, sigma lambda k 2 plus lambda k plus 1 minus lambda k. So my eigenvalues are mu1k 2k equals 1 divided by 2 trace plus trace square minus 4 the determinant. So I know that if sigma is greater than sigma 1, then everything is a sink. But I'm concerned here with what's going on when k is going to infinity. So we are going now to do the computation. So I get for the details. So let's do trace square equals so I get lambda k square as for okay, so at this point, I give you the path. I need to write this down in such a way that I want to prove that there exists so assume sigma greater than sigma 1. Then there exists some mu such that for all k in n, the real part of mu1k is less than mu, and the same thing for mu2k. And actually, almost all of the eigenvalues are real. Okay, with that in mind, now, if I have that, I can look again at this quantity. Which is the norm L2. But in fact, I can do a little bit better because I know that so if I write, let's say UK is UK VK, I know that by a change of variable, so let's consider only the large K, I can write UK equals P UK tilde and UK tilde tilde of T will be equal to UK tilde 0 exponential minus mu 1K of T, and VK tilde of 0 equals exponential minus mu 2K of T. All right, so sorry, it's a plus, but with mu 1K and mu 2K, real negative numbers. And so at the end of the day, I can obtain that I know that UK of T equals P times UK tilde. And so the point is to prove that I can ensure that I have also UK T square plus VK T square will be less than exponential minus some, let's say, delta T U. It's not the K now that I want, it's the sum. So I want to prove that, and I know these things from the analysis of the ODEs. So what I would like to do for you to do for the next week is to try to prove this thing. So if we have this thing, then so for sigma greater than sigma 1. So if you have this thing, then we got the result. So I want to go you through the details and prove this thing. There is a simplest way to prove the result of theorem 1 without using all the details. But if I use this technique to prove the theorem, I will lose this exponential decay. And sometimes we won't be able to prove that, but in this case, since we have the estimate mu 1K, mu 2K is less than mu is less than 0, we can prove that, okay?
Meeting is being recorded.
Okay, so now let us try to make some numerics about the PDE. So for that, we are using a C++ program. So let's use it. So here, this is my program. So I have here a CPP file along with a H file, header file. And so for the header file, which is here, I will show you where the things appear. So first, yeah. So here, it's a little small, but hopefully you can see it. I will change the du, which corresponds to the sigma. So let's say, so we want a sigma which is bigger than sigma 1. Sigma 1, it's p square. So let's say I take to be 10 or 15. Let's say 10. Here I define my function. So this is not exactly the same. So my system was u minus v and 3 minus 2y. Okay, the reactive part. Okay, guess I'm good. So now I'm running the program. So exit. So the C++, so I need to save, of course. The C++ program is called oh, I have a problem. Okay. Why is that? Maybe I chose. This is too big, maybe. Yeah. So okay, let's do it simple. Hopefully I just changed that. I think this is too big. Right? It's very fast. Let's take a bigger time. Yeah, but yeah, it doesn't work. It's But now, so I just playing with the time on which I simulate, which is my capital T. This is the horizontal space times space step, and this is the time step. So we have to wait a little bit. So meanwhile, I'm having a look at this one. Okay. So a few comments on that. So when I look at when you look at this file, you can see that I'm writing on this text file, that data file. So now I'm going to run this one. I run this one too, and when I run this program, I will write in the file which is called named fic.txt. So let's now run. Sorry. Okay, finally, I go to GNU plots. So this is the solution of my PDE. I don't know if you saw a lot. Let's do it again. I'm showing you the solution of the PDE. So the PDE is defined on 0, 1, and I'm showing U as a function of T. You can see that everything goes to 0. All right, now I will decrease the value of sigma. And if I decrease the value of sigma, oh yeah, I know what I did. So so sigma one is lambda k minus 1. There's computation, but yeah, I didn't need to take a so big du. Because my sigma 1 is less or more 0.1. So let's look at this. So now I will decrease my du. So this was huge. Let's take 1. So it looks like everything still goes to zero, which is what is to be expected. So the initial condition are C7, C7. To have a look at what is C7, C7. We need to go there. Okay, so C7 is that. For NB. Okay. Okay, so it's still going to zero. So I'm still decreasing my sigma, and according to the theory, when I reach a value sigma such that sigma is small enough, I have a change is that the solution doesn't go anymore to zero. So let's choose here 0.02 for example. Oh, you see? Now, just looking at these values, you see that my u, so here are some values of u, they're not going to zero anymore. All right, so let's have a look at the movie. Actually, I don't think I need to. Yeah. So again, I can do it again. Okay, you can see that yeah, the solution, you see that is going to it's going to infinity. Okay, so that reflects our theoretical work. I took so my at the beginning my sigma was too large, so I had problems of convergence of the solution. So I can do that maybe. Hopefully it's not too, and that, and 20 maybe is sufficient here. Let's say what do we get? Yeah, so it will take a while. Yeah. Hopefully this works. Yeah, it takes a while. Yeah. Yeah, so my discretization was worth. So I tried just to take a smaller space step, but then, okay, so let's look at the solution now. Yeah. Right, it's the same. So, all right, so last one, I know I'm going to increase. I will choose 0.2 again, so that you can see the difference here. So my parameter sigma is this one, okay? So I expect now the solution to go to 0, but let's see. Yeah, looks good. All right, so we are going to stop the class now. So we did some theory, and then we performed some numerical simulations. And the results of the numerical simulation show that when our value sigma is decreased, the qualitative behavior changes, because you see that the PDE for sigma large goes to 0, while at some point it goes to infinity. And so that supports our theoretical work. So that's good. All right, so that's it.